A single invisible particle can pass through your body right now and leave damage that may never fully heal. You would not feel it, you would not see it, but deep inside your cells, something critical would already be breaking apart. Space is not silent, it is not empty. It is filled with high-energy radiation moving at speeds close to the speed of light. These particles come from exploding stars, distant galaxies, and violent cosmic events that most people will never think about. They cross the universe without slowing down. And when they reach a human body, they do not stop at the skin. On Earth, you are protected. A powerful magnetic field surrounds the planet. A thick atmosphere absorbs most of the radiation before it can reach you. These layers act like a shield that has kept life safe for millions of years. Without them, life as we know it would struggle to survive. The moment you step outside that protection, everything changes. Interstellar radiation is not like the radiation people usually think about. It is not just a weak exposure over time. It is made of particles so energetic that they can pass through metal, spacecraft walls, and human tissue as if they barely exist. Some of these particles are heavy ions. They carry enormous energy. When they collide with atoms inside your body, they create microscopic explosions along their path. This is where the real danger begins. Most people expect radiation to burn or cause pain right away. That is not how this works. Interstellar radiation does something far more unsettling. It moves through you silently. It interacts with your cells at a level too small to notice, and it begins to damage the very code that keeps you alive. Your body is built on a delicate system. Every cell carries instructions. These instructions are written in DNA. That DNA controls how cells grow, repair, and function. When high-energy radiation strikes, it can break those instructions apart. It can snap DNA strands. It can alter the structure of molecules. It can leave behind errors that your body cannot always fix. Here is the part most people do not know. The damage does not always show up immediately. You can feel completely normal while serious changes are already happening inside you. Cells may begin to malfunction, some may die, others may survive, but carry mutations. Over time, those mutations can lead to diseases like cancer. The process can take years, sometimes decades, but the effects are not limited to DNA. Radiation can reach the brain. It can interfere with neurons, the cells responsible for thought, memory, and decision-making. Studies suggest that prolonged exposure can reduce the brain's ability to form new cells. This means memory can weaken, focus can decline, reaction times can slow down. In extreme conditions, even behavior can change. This is one of the biggest hidden threats of deep space travel. Astronauts who travel beyond low Earth orbit face a level of radiation that is far higher than anything experienced on the ground. Even with shielding, they are exposed to a constant stream of cosmic particles. Over long missions, the exposure builds up, the risk increases with every passing day, and there is another layer to this problem. Interstellar radiation does not hit all parts of the body equally. Some particles pass straight through without causing much damage. Others collide directly with critical molecules and cause severe disruption. This randomness makes it difficult to predict exactly how the body will respond. Two people exposed to the same environment could experience very different outcomes. That uncertainty is what makes it so dangerous. The human body evolved under the protection of Earth. It was never designed to handle this kind of environment. And every system inside you, from your immune system to your cardiovascular system, depends on stability. Radiation introduces chaos at the smallest level. Over time, that chaos spreads. Even short exposure can have measurable effects. Longer exposure can become life-threatening. Scientists have been studying this problem for decades. They have used advanced simulations and experiments to understand how radiation interacts with human tissue. The results are concerning. Even low doses, when extended over time, can lead to significant biological changes. High doses can cause acute damage that appears much faster, and yet this is only the beginning of the story, because the real question is not just what radiation is. The real question is what it does to you step by step. From the moment a particle enters your body to the long-term consequences that follow. The process is far more complex than most people realize. In this video, you will learn exactly what happens inside your body when interstellar radiation hits you. You will understand how these particles move through tissue. You will see how they break down DNA and disrupt cells. You will discover how the brain is affected, how vital systems begin to weaken, and why this invisible threat is one of the biggest challenges in human space exploration. You will also learn why this problem is still not fully solved and why it could determine the future of missions beyond our solar system. Some of the facts you're about to hear are rarely discussed outside of scientific research. They reveal a side of space that is far more hostile than most people expect, a side that operates quietly, without warning, and with consequences that can last a lifetime. This is not about sudden destruction. This is about slow, invisible damage that builds over time. And by the end of this video, you will understand why interstellar radiation is not just a technical challenge. It is a biological barrier that humanity must overcome if it ever wants to travel deep into the universe. Welcome to the channel. If you want to explore the hidden dangers of space and the science that shapes our future, make sure you subscribe and stay with us. The first contact does not feel like anything. There is no heat, no pressure, no warning. A high-energy particle from deep space reaches your body and passes straight through your skin as if it is not even there. These particles are not slow. Many travel close to the speed of light. Some are simple protons, others are heavy ions, atoms stripped of their electrons and turned into dense, fast-moving projectiles. When they arrive, your body does not stop them. Skin offers almost no resistance. Muscle, blood, and bone do not slow them down in any meaningful way. On Earth, radiation exposure often comes in small, controlled doses. It spreads out, it loses energy quickly. In deep space, the rules change. These particles carry so much energy that they cut through the body in a straight path. Scientists sometimes describe this as a microscopic bullet, but that comparison is still too weak. A bullet damages tissue along a visible path. These particles leave behind something far more subtle and far more dangerous. As the particle moves through you, it begins to interact with atoms inside your body. Atoms are normally stable. Electrons orbit around a nucleus in a balanced system. That balance is essential for every chemical reaction that keeps you alive. The moment a high-energy particle collides with one of these atoms, that balance K's electrons are ripped away. This process is called ionization. It happens in a fraction of a second. One atom becomes unstable, then another, then thousands more along the particle's path. Each interaction creates a tiny disruption. Alone, each one seems insignificant. Together, they form a chain of damage that spreads through your cells, inside your body. Everything depends on precise molecular structures. Proteins must hold their shape, cell membranes must remain intact, DNA must stay organized. Ionization begins to interfere with all of this. Bonds between atoms weaken, some break completely. Molecules that once worked perfectly start to malfunction. This is not a slow process. It begins within milliseconds of exposure. There's another detail that makes this even more dangerous. When a high-energy particle strikes an atom, it can create secondary particles. These are smaller bursts of energy that spread outward from the original path. Instead of a single line of damage, you now have a branching pattern. A cascade of microscopic disruptions spreads through nearby tissue. This means one particle can affect far more than a single point, and still you feel nothing. There is no pain signal for this kind of damage. Nerves do not react to ionization at this scale. Your body remains unaware while critical structures begin to change. This silent nature is what makes interstellar radiation so deceptive. The damage starts instantly, but it hides beneath the surface. In deep space, this is not a rare event. It is constant. Streams of cosmic radiation move through space at all times. There is no atmosphere to absorb them. No magnetic field strong enough to deflect them completely. Even inside a spacecraft, many of these particles still get through. Shielding can reduce exposure, but it cannot eliminate it. This means your body is not dealing with a single impact. It is dealing with repeated hits, again and again over long periods of time. Each particle leaves behind a trail of ionized atoms. Each trail adds to the total damage. Over time, these microscopic events begin to overlap. The body tries to maintain order, but the disruptions keep coming. And as this invisible assault continues, the damage moves deeper towards something far more critical than atoms and molecules. As the damage moves deeper, it reaches the most sensitive part of every cell, DNA. This is the code that controls everything inside you. It tells cells when to grow, when to repair, and when to stop. It holds the instructions that keep your body stable and alive. When interstellar radiation reaches this level, the effects become far more serious. The high-energy particles do not slow down when they approach DNA. They strike it directly. The structure of DNA is delicate. It is made of two strands twisted together in a precise pattern. That pattern must stay intact for cells to function correctly. Radiation breaks that pattern. Some hits cause single-strand breaks. One side of the DNA ladder snaps. Cells can often repair this type of damage, but even then, mistakes can happen. Other hits are far worse. They cause double-strand breaks. Both sides of the DNA are severed at the same point. This is much harder to repair. In many cases, the cell cannot fix it correctly at all. This is where things begin to go wrong. When a cell tries to repair broken DNA, it follows a process. It reconnects the strands and restores the structure, but under constant radiation exposure, the system becomes overwhelmed. Repairs become rushed, errors slip through, small changes appear in the genetic code. These changes are called mutations. Some mutations are harmless, others are not. A single incorrect change in DNA can alter how a cell behaves. It can force a cell to grow when it should. Not, it can disable the signals that normally stop damaged cells from dividing. Over time, these small changes begin to accumulate, and this process starts almost immediately. Within moments of exposure, cells begin to carry altered DNA. Some cells detect the damage and shut themselves down. This is a protective response. The body sacrifices those cells to prevent further harm, but not all cells respond this way. Some survive with damaged DNA. These cells continue to divide. Each time they replicate, they pass the mutation forward. This creates a growing population of defective cells inside the body. At first, the number is small. It may not affect anything noticeable, but with continuous radiation, the number increases. There is another layer to this damage that is rarely discussed. Radiation can also affect the way genes are turned on and off. Even if the DNA sequence is not completely broken, the control systems can be disrupted. This can lead to abnormal protein production. Cells may begin to behave in ways that are unpredictable and unstable. Over time, the risk becomes clear. The accumulation of mutations is one of the primary causes of cancer. Cells that should stop growing continue to divide. Cells that should die remain active. Tumors can begin to form long after the original radiation exposure has occurred. This delay makes the danger even harder to detect. And in deep space, the exposure does not stop. The body is constantly trying to repair itself. At the same time, new damage keeps appearing. It becomes a race between repair and destruction, a race that the body is not designed to win under these conditions. As more cells become damaged, the effects begin to spread beyond DNA alone. Entire systems start to feel the impact, and one of the most vulnerable systems lies within the brain, where even small changes can alter how you think, remember, and respond. Senin, the damage does not stop at the body. It moves upward past bone and tissue and reaches one of the most protected organs you have. The brain, the skull feels solid. It feels like a barrier. Against interstellar radiation, it is almost meaningless. High-energy particles pass through bone just as easily as they pass through skin. They reach brain tissue without slowing down, carrying enough energy to disrupt cells that control thought, memory, and behavior. Inside the brain, everything depends on precision. Billions of neurons communicate through tiny electrical signals. Each signal must travel along exact pathways. Each connection must remain stable. Even a small disturbance can affect how the brain functions. Radiation introduces that disturbance. When these particles pass through brain tissue, they damage neurons directly. Some neurons are destroyed on impact, others survive but lose their ability to communicate properly. The structure of these cells changes, their connections weaken or break. Signals that once moved smoothly begin to slow down or get lost. This is not something the brain can easily repair. Unlike many other cells in the body, neurons do not regenerate quickly. Some regions of the brain can produce new neurons, but the process is limited. It is called neurogenesis. Interstellar radiation interferes with this process. It reduces the brain's ability to replace damaged cells. Over time, the balance shifts. More neurons are lost than replaced. This leads to gradual decline. Memory is one of the first functions affected. The brain struggles to store and retrieve information. Small details begin to fade, patterns become harder to recognize. Tasks that once felt simple require more effort. This change can be subtle at first, but it grows with continued exposure. Decision-making also begins to weaken. The brain relies on fast and accurate processing to make choices. When neurons are damaged, that process slows down, reaction time increases, judgments become less precise. In high-risk environments like space, even a slight delay can have serious consequences. There is another effect that is even more concerning. Radiation can alter behavior. Studies suggest that exposure to high-energy cosmic particles can affect emotional regulation, anxiety levels can rise, mood can shift without clear reason, confusion can appear in situations that once felt familiar. In some cases, the ability to assess risk becomes impaired. This means a person may make decisions that are not just slow, but also dangerous. This is rarely discussed outside scientific research. The idea that radiation can influence how a person thinks and behaves is unsettling. It turns a physical threat into something deeper. It affects identity, perception, and control. The brain is not just being damaged, it is being altered, and this happens without any immediate warning. There is no sudden signal that tells you your brain is under attack. The changes build over time. Each passing particle adds a small amount of damage. Each damaged neuron reduces the brain's efficiency. Slowly, the effects begin to stack. In deep space, where exposure is constant, this becomes a serious problem. The longer the mission, the greater the risk. Cognitive decline is not just a personal issue. It affects performance, safety, and survival. As the brain struggles to maintain control, the rest of the body begins to feel the pressure. Systems that depend on coordination and stability start to weaken. The damage spreads beyond thought and memory, reaching vital functions that keep the body alive. The damage does not stay isolated. It spreads through the body, moving from cells to entire systems. What began as microscopic disruption now starts to affect how the body functions as a whole. The immune system is one of the first to weaken. This system depends on fast cell production and precise coordination. White blood cells are constantly created to detect and destroy threats. Interstellar radiation interferes with this process at its source. It damages the bone marrow where many of these cells are produced. When production slows or becomes unstable, the number of active immune cells begins to drop. At the same time, existing immune cells can become defective. Some lose their ability to recognize harmful invaders. Others respond too slowly. This creates a dangerous imbalance. The body becomes more vulnerable to infections that it would normally handle with ease. Even minor bacteria can become a serious threat when the immune system is weakened. There is another effect that is less visible but equally serious. Inflammation begins to increase. Radiation can trigger chronic inflammation inside the body. This is not the short-term response that helps healing. This is a long-lasting state that slowly damages tissues. It adds stress to organs and disrupts normal function. Over time, this constant internal strain begins to take a toll. The cardiovascular system is also affected. Blood vessels are lined with delicate cells that help regulate blood flow. Radiation damages these cells. The walls of arteries begin to stiffen. They lose flexibility. This makes it harder for blood to move efficiently through the body. The heart has to work harder to maintain circulation. This increased effort puts the heart under stress. Over time, the risk of serious conditions rises. Blood pressure can become unstable. The chances of heart disease increase. These changes do not happen instantly, but they build steadily under continuous exposure. The digestive system faces its own challenges. The lining of the gut is made of rapidly dividing cells. These cells are constantly replaced to maintain a healthy barrier. Radiation disrupts this cycle. Cells are damaged faster than they can be replaced. The lining begins to degrade. This can lead to problems with nutrient absorption. The body may struggle to extract the energy it needs from food. At the same time, the weakened barrier allows harmful substances to pass through more easily. This adds further stress to the immune system, creating a feedback loop of damage. Blood production becomes unstable as well. Red blood cells carry oxygen. White blood cells fight infection. Platelets help with clotting. All of these are produced in the bone marrow. Radiation interferes with this process, Production becomes irregular. Some cell types may drop in number, others may form incorrectly. This imbalance affects the entire body. Oxygen delivery becomes less efficient, healing slows down, the ability to respond to injury is reduced, even small wounds can take longer to recover. As these systems begin to fail, the overall effect becomes clear. Energy levels drop. Fatigue starts to set in. This is not normal tiredness. It is a deep, persistent weakness. The body is working harder just to maintain basic functions. Every system is under stress at the same time, and while these effects grow stronger, there is still no clear signal that points to a single cause. The damage remains hidden, building quietly beneath the surface as exposure continues. The most dangerous part of this process is how quiet it is. There is no pain when radiation passes through your body, no clear signal that something is wrong. No immediate reaction that forces you to stop. Everything feels normal on the surface. Breathing stays steady. Movement feels the same. The body gives no warning. But underneath that calm, damage continues to build. Each particle that passes through leaves behind a trace, a broken bond, a damaged cell, a broken bond, a damaged cell, a small error in DNA. On its own, each event is almost meaningless. The body can repair many of these small injuries. It is designed to handle limited damage. The problem is not a single event. The problem is The problem is accumulation. Interstellar radiation does not arrive once and disappear. It is constant, a steady stream of high-energy particles moving through the body over long periods of time. Each one adds to the total damage. Each one increases the burden on the body's repair systems. At first, the body keeps up. Cells repair themselves, damaged components are replaced, everything continues to function. This creates a dangerous illusion. It feels like nothing is happening. It feels like the body is unaffected, but the repair systems are not perfect. Small mistakes begin to slip through. A repaired DNA strand is not exactly the same as before. A cell that should have been removed survives instead. Over time, these small errors begin to stack on top of each other. This is where the silent effect becomes visible. Symptoms do not appear right away. They can take days, sometimes months, in many cases years. The delay makes it difficult to connect cause and effect. By the time the damage becomes noticeable, it is already deeply embedded in the body. This delayed response is one of the most unsettling aspects of radiation exposure. A person can feel completely healthy while serious changes are already in progress. Cells may be mutating, tissues may be weakening, systems may be under stress. None of it is obvious in the moment. There is another detail that increases the danger. Long-duration exposure is far more harmful than short bursts. A brief exposure may cause limited damage that the body can repair. Continuous exposure does something different. It prevents full recovery. The body is forced to repair damage while new damage is still occurring. This creates a constant state of strain. Over time, the balance shifts. Repair becomes less effective, damage becomes more dominant. The body starts to lose its ability to maintain stability. This transition is slow, but once it begins, it is difficult to reverse. This is the reality faced by astronauts in deep space. Missions beyond Earth's protective field expose them to radiation for extended periods. Every day adds to the total dose. Every hour increases the risk. Even with protective measures, the exposure cannot be completely avoided, and the longer the mission, the greater the accumulation. This compounding effect means that risk does not grow in a straight line, it accelerates. Small increases in exposure time can lead to much larger increases in damage. This makes planning long-term missions extremely difficult. The body does not fail all at once. It changes slowly, quietly, step by step. And by the time the effects are finally clear, the damage has already reached a level that cannot be ignored, pushing the limits of what the human body can endure in an environment that never stops applying pressure. This is where the problem becomes bigger than the human body. It becomes a barrier to exploration itself. Modern spacecraft are built with advanced materials. They are designed to handle extreme temperatures, pressure differences, and micrometeoroid impacts. But when it comes to interstellar radiation, even the best shielding falls short. Most shielding works by absorbing or slowing down incoming particles. This can reduce the energy before it reaches the body. It works well against lower energy radiation. But interstellar radiation is different. Galactic cosmic rays carry enormous energy. Some are heavy ions that move so fast and hit so hard that they pass through shielding with only partial loss of energy. In some cases, shielding can even make the situation worse. When high-energy P particles strike the outer layer of a spacecraft, they can break apart into secondary radiation. This creates a cascade of smaller particles that spread inside the structure. Instead of blocking the threat, the shielding turns one particle into many. Each one continues through the interior, increasing overall exposure. This is a lesser-known challenge that engineers continue to struggle with. Adding more shielding is not a simple solution. Thicker materials increase weight. More weight requires more fuel increase mission complexity and cost. There is a physical limit to how much protection can be added before the mission becomes impractical. Even with improved designs, complete protection remains out of reach. This leads to a critical problem. Even small doses of radiation, when extended over time, exceed safe limits for the human body. Space agencies set strict exposure thresholds for astronauts. These limits are based on the risk of cancer and other long-term health effects. Missions that go beyond low Earth orbit already push close to these boundaries. Interstellar travel would go far beyond them. A journey to another star would take years, possibly decades, with current or near-future technology. During that time, the crew would be exposed to continuous radiation. The total dose would build to levels that the human body is not designed to handle. This shifts the challenge from engineering to biology. The question is no longer just about building faster engines or stronger spacecraft. The real question is whether the human body can survive the journey at all. Every system inside the body has limits. Radiation pushes those limits from the inside out. It damages cells faster than they can recover. It weakens systems that are essential for survival. Technology can solve many problems. It can extend life support. It can create artificial environments, but it cannot easily rewrite human biology. This is why radiation is considered one of the biggest unsolved problems in space exploration. Scientists are exploring possible solutions, advanced materials, magnetic shielding that mimics Earth's protective field, biological countermeasures that repair or resist damage. Each idea shows promise, but none provide a complete answer yet. Time remains a major factor. The longer the journey, the greater the exposure. The greater the exposure, the higher the risk. This creates a hard limit on how far humans can travel safely with current knowledge. Deep space is open, the path exists. But the human body stands at the edge of that path, facing an invisible force that does not stop, does not weaken, and does not negotiate. Interstellar radiation is not just a distant threat. It is a constant force that attacks the human body at its most basic level. It moves through skin, breaks atoms, damages DNA, and slowly weakens the systems that keep you alive. The danger is not loud or immediate. It is silent, steady, and deeply internal. This is why the dream of traveling between stars faces a serious limit. Spacecraft can be stronger, engines can be faster, missions can be longer, but none of that changes what happens inside the human body during the journey. Shielding is not enough. The particles are too powerful, the exposure lasts too long. Even small doses repeated over time push the body beyond what it can safely handle. The real barrier is not distance, it is biology. The human body evolved under the protection of Earth. Away from that protection, it begins to struggle. Cells break down faster than they can repair. Systems lose stability. The longer the exposure, the harder it becomes to recover. This turns deep space into an environment that works against human life at every level. And this problem is still not solved. Scientists continue to search for answers. New materials, new technologies, and new ideas are being tested. But for now, the path to interstellar travel remains blocked by something invisible and relentless. The universe may be open, but the human body is not yet ready to cross it. If this changed the way you think about space, take a moment to support the channel, like the video, and subscribe for more deep science content that explores the limits of reality and the future of humanity.